Our next speaker is Professor Saurabh Singh. He did his BTech from IIT Dhanbad and later joined RRI as PhD fellow. Then he moved to McGill University, Canada for his postdoc. Recently, in 2022, he joined RRI as a faculty member. His research interests include experimental cosmology, and today he will be talking on peering into early universe.
Hi everyone, a very good morning. So we'll shift gears and go from local universe to moderately early universe. And I'd mostly be talking about the kind of activities we are doing at RRI towards designing these very custom telescopes to be able to observe these very specific epochs in the early universe. But before I dive deep into those details, a big shout out to all the team. So I'm really representing a body of work on behalf of a huge team members. The current members are listed here, along with a lot of support from electronics and mechanical engineering services, different observatories around, and also the continuous stream of VSP students, many of who are here in the audience. So with this, let's get started. This is just a chart of all different interesting events that happened in the process of evolution of the universe. So we know a lot about CMB, which is this black body curve that we all love. And with all these anisotropy measurements from WMAP and Planck, we have been really able to constrain this epoch of recombination right here. And then we have made a lot of progress to study our local universe. Many of the talks have covered that. But the process in between is really very unconstrained. So it's like you're looking at an infant and an adult, and you really want to figure out rest of the time span, and this is a very non-linear process. So there are lots of interesting epochs in between, starting off with formation of very first stars, which is what we call as cosmic dawn here. And basically the ionizing radiation from them, ionizing the intergalactic medium, which is epoch of free ionization. And then finally we have structure growth, and finally leading to expansion of the universe at a very accelerated pace. So I don't have time to cover all of these. So today I will mostly be focusing on this epoch right here, which is the boundary from formation of first stars to the radiation from them ionizing the universe. A very simplistic picture of that process is right here, which is we have really just gas and photons in the very early part of the universe, which we call as dark ages, and there is very minimal interaction between them. That seems to change when we have these very first stars forming, because we have these gravitational instabilities, we have overdense regions, and that leads to formation of these very first structures. And radiation from these structures starts to ionize the gas around them. But in the very early part of the universe, we're talking about some 400 million years after Big Bang, these processes are very local, and simply because there is so much gas around that it's also competing with recombination. But what really happens later as more and more sources form, these tiny bubbles of ionization start to overlap, and that really accelerates the whole process by which universe reionizes. And at around redshift of 6, which corresponds to around say 7 to 900 million years after Big Bang, we have sufficient evidence that the entire universe, and we're talking about intergalactic medium here, is almost completely ionized. So there are lots of questions in this period right here, starting off when the first stars actually formed, and given the environment in which they formed were very different from our local universe, what kind of processes led to them. So for example, what were the cooling mechanisms, or what was the minimum mass that really led to formation of the very first stars. And finally, there are different models of inside out and outside in reionizations, and how say heating of the IGM took place, and a lot of sub-processes that started off right at cosmic dawn and went on till epoch of reionization. So all these questions, yeah.
Why does ionization happen? Why does, just from very basic questions of that sort?
Sure. So basically these sources of radiation emit a range of photons from X-rays to UV. And these UV photons, Lyman alpha photons primarily, are the ones, if they escape the halo, they are able to ionize the gas.
So what one is seeing is you're seeing radiation, but how can you tell whether it's coming from an ionized or a not ionized?
Right. So
neutral background.
Right. So basically, and that's really the next slide, which is we are looking at emission from the neutral hydrogen. So we are essentially looking only at the neutral gas, absence of which will be basically the ionized regions. So in some way we are mapping the distribution of the gas itself. Yeah, I have some pictures. Hydrogen is formed around here when the protons and electrons combine, which is the CMB epoch.
Okay, so that's okay.
Redshift of around 1100.
So that's like in that other figure.
Or somewhere
Just
here.
okay,
Yeah.
somewhere there.
And why the first stars? What are the elements? What's the highest? What's the heaviest element that's formed by then?
Yeah. So basically, at around nucleosynthesis, we only expect hydrogen, helium, and traces of lithium. That's all.
And then at the first stars, you've already started to have.
Right. So when these first stars go supernovae, then we have production of heavier elements. But the very first generation was formed in a very metal poor environment, and that's really the mystery.
But metal poor. But it's basically still just hydrogen,
yeah.
helium, and lithium.
That's it.
At that point,
Yes.
first stars, nothing else.
Nothing else, and that's really the problem because you need heavy metals to form stars so that they can cool, right?
Yeah.
They are cooling agents, so it's like a chicken and problem. But you need stars to form those. So the formation, the very first formation itself, I mean, in some way, hydrogen atom itself can act like a coolant, but that's a very poor agent. So yeah, formation of first stars itself is
So should we call them stars at all, or just clumps?
no, they are pretty much stars. Yes, and tying up to the kind of signals we are looking for, we can actually probe how they formed. So by probing what was the minimum mass of halo that was required to form stars, which is tied up with what cooling elements were present.
Dark matter.
No, this is all baryonic matter. Like what kind of cooling mechanisms can be supported at those high redshifts. Dark matter would come up to create the potential wells. Okay, so yeah, so in order to probe all these different epochs, we employ 21 centimeter radiation. And of course, this audience probably doesn't need an introduction to this. It's a spin flip transition of hydrogen atom. So essentially what we are tracing is presence of hydrogen. And what we are measuring is the brightness temperature. So why prefer this over all these different observables that we have? There are two very distinct advantages. The first is the span of time that it allows us to probe. So when we look at early universe through other means, say optical or infrared, we are really at some point get limited by sensitivity. So Hubble or say JWST now has gone on to say redshift of 10. We heard talk from Biman yesterday. But using 21 centimeter radiation, we can probe redshifts all the way to 30 and sometimes 50 in principle. So that's first. And the second thing is it also allows us to probe the temporal evolution. Because what happens is its rest frame frequency is 1420 megahertz. And as it comes to us, it also redshifts. So based on which frequency we are looking at, we are probing a very specific cosmological redshift. So in some way, we can literally study the entire evolution of different parameters by studying the 21 centimeter radiation. This is unlike, for example, in CMB, we study optical depth, which is an integral from that epoch to us. So it becomes very model dependent to reconstruct things from there. While here we have very fine time information and spatial information. So what do we really measure when we measure brightness temperature of hydrogen? It really is a very complicated process. It's an entire radiative transfer actually. But I'll just point out to two very specific parameters that we are sensitive to. The first is neutral fraction. So we definitely need hydrogen to be able to detect 21 centimeter. So as the neutral fraction of hydrogen goes, the strength of the signal also reduces. That's very natural. But that basically means that we can use this to trace the ionization history of how quickly or how slowly the universe ionized. And the second parameter, which is right here, is TS, which is the spin temperature. Spin temperature is just the ratio of population of triplet and singlet states, but it also couples to other physical temperatures under some conditions. So the spin temperature can couple to the gas temperature or it can couple to the background radiation temperature, and both of these will play a very critical role later in the slides. So we are also able to trace the thermal history, and these temperatures in turn depend on the first sources and how the radiation propagation happens. So in some way we can construct models and generate different templates of how the brightness temperature would change with redshift, or here redshift it also corresponds to frequency. So how the signal will look like at different frequencies. So these are the two very important parameters that we'll touch upon later in the talk. Now the question is, how do we measure this? And there are various ways. Fundamentally, what we are trying to do is to measure a field, and this field is basically the brightness temperature field. So we are looking at intensity of 21 centimeter radiation at different times. So all these vertical slices are basically different times corresponding to different redshifts or time. While at a specific time, what we are looking at is the spatial distribution. So of course, universe has density fluctuations, and as the stars form, it's not very uniform across. So you can see, for the example, the patchiness that we see here. So, and both of these are interesting properties. So given this field, for example, what are the statistical measures that we can come up with? The very fundamental measure is just the mean, right? So we can look at the mean intensity at a given redshift and plot that as a function of redshift or frequency, which is what we call as the global signal. So this is just a single number at every redshift. And the spectral nature of this signal really captures a lot of information about various sub-events that happened along this. But that's not really the complete story. It's definitely non-Gaussian field, so other moments also have a lot of interesting information. We can also measure power spectrum, and basically that allows us to measure these fluctuations or the variance of the field. And there are different experiments trying to do that. I'll be talking actually both about the power spectrum measurements and also the mean measurements. From an observational point of view, mean measurement is really very simple in construction. It really requires just one antenna which has to undergo an absolute calibration, because really we are basically making a thermometer and measuring the sky temperature.
So you got this plot using the equation, the brightness temperature equation that you showed in last time?
Yes, but what we need is a prescription for ionization and prescription for spin temperature evolution. And of course,
Are these three parameters?
no. One has to start from an astrophysical scenario. So you have to basically plant some stars, prescribe what the luminosity function is, the radiative transfer, and from there you get how the spin temperature evolves.
You have planned some stars.
Yes.
In that case, you are putting all the assumptions.
Yes.
You want
Yes.
to build
And show what the free parameters are. So they are more about the halo properties rather than directly putting it as a spin temperature property.
Yeah. What part of this curve has been experimentally verified actually?
This whole signal is as of now undetected.
The entire, over all those frequencies, there's nothing which we can actually verify?
No.
Okay, fine, thanks.
The only thing is not 21 centimeter, but when the signal ends, which is basically us saying that hydrogen is completely depleted, we have some other observations from quasars that also kind of hint that, okay, we don't have a hydrogen by the redshift of 6 or around 200, but using 21 centimeter, we really have nothing right here. And sufficient reasons why, which is basically the point of my talk. So in order to measure, sorry, yeah.
There was this VLA 74 megahertz sky survey, and did not that produce anything?
VLA survey.
Initially they started low frequency,
Right.
74 megahertz. So
They have some upper limits. They are limited by systematics. I think there is OVRO survey, which was done at even 30 megahertz for that matter. But these are right now just limited by their own calibrations. And the maximum one can do is put an upper limit of how high the signal can be. But there has not been a detection yet.
Okay. Another question is that you told that when reionization will begin, there will be depletion in the H1. But here it depletes at redshift of 20. But we know that reionization fully grown at around 10 to 8 redshift.
Right.
So why this is happening?
The question of 8 and 10 I think comes from CMB studies, right? The optical depth measurement. They assume an instantaneous reionization because optical depth needs the integral under area of xh1 is a function of z. So you can get the same optical depth by using different functional form. So the number of 8 that's quoted is basically if you assume it's just instantaneous process in which the entire gets depleted all at once. But if you can get the same area under different models of how the xh1 actually reduces, and unfortunately optical depth cannot do that because it has no time information.
Very basic question. I think it's probably just a definition how you are defining this thing. So what does this negative thing mean actually? You are saying that this is just a density, right, or some form of density. So negative means what actually?
Yeah, right.
Yeah. So what is this? This thing? TS is what?
So for epochs here, Ts is basically our gas temperature,
Okay.
and Tr is the background temperature.
So it is with respect to the background temperature
Yes.
you are
It's a
measuring.
differential measurement in some way.
Okay.
You are measuring the contrast between the gas temperature and the background temperature.
And that background temperature is not the CMB temperature. So it's with respect to the CMB temperature.
Yes.
Okay.
So negative really just means that the gas is cooler than CMB. Yeah, so in order to measure the monopole or the mean, in principle, a single antenna should do, because we are measuring over a very broad range of sky. That's not true for power spectrum, where we also want to measure the variance, because then we also need fine angular resolution on the sky to be able to cross correlate things. And that's where we need a lot of elements put together. So experiments like HERA are custom designed to be doing that, which I'll talk about later, and upcoming SK also has one of the key science goals of detecting this power spectrum from cosmic dawn and epoch of reionization. Right, and this comes back to the questions about how we generate this. So we have different prescriptions from the astrophysical properties of the very first stars. So different colors here really just shows the ratio of their Lyman alpha flux to X-ray emissivity. And because they are completely unconstrained, we are at liberty to vary as much as we want. And that basically produces different signatures of how the 21 centimeter radiation looks like, the mean component of it. And there is a similar prescription for power spectrum. Yeah, so basically you change their X-ray efficiency heating of how well can they heat the IgM, and also how much Lyman alpha actually escapes the halo. Just by changing that, you get a series of things. The deeper these troughs means the cooler the IgM is. So poor the X-ray heating is. Yeah. This part. So basically, the moment it starts to reduce is when, at a global level, we start to have ionization of the gas. The parts are mostly towards heating of the IgM. So there are small sub-processes. Ionization is basically this part. I would say around a redshift of between 15 and 10 going up to 6. But these are under very standard lambda CDM regimes. Lately, there has also been a lot of work to incorporate a lot of exotic physics. And since Sanjeev asked about the background temperature, initially the assumption was that this could just be the CMB, but people have also worked out what if we have some excess background because of the radio population at those redshifts, again something which is very unconstrained. So people take liberties, and basically because if this is high, the contrast increases, so you would have even deeper absorption troughs, right? Because the gas temperature just cools adiabatically. And that basically gives rise to huge absorption depths, more than what just CMB can offer. So there are lots of non-standard models also that can be, and this is really good for an experimentalist, because those are much easily ruled in or ruled out compared to less amplitude models. But at the end of the day, we would really want to probe all of these models.
I mean, these are produced using some simulations, like structure formation simulations?
Right. So different, there are n-body simulations, there are also semi-numerical simulations. This was just a semi-numerical prescription. But how do you incorporate that excess is again very model dependent. The way this is done is you have luminosity function in radio calibrated to the present universe, and you have free parameter F radio, which you basically blow up to create more and more excess in the early universe with some redshift dependence. So that's just a prescription that people have used.
On the right side, right? No, in the simulation, yeah. So
These ones?
No, there's one of them has a very sharp edge like that of this Bowman's curve. No, left side
ones?
simulation. In the left side one.
Oh, this one?
Yeah.
Oh, this is an interpolation problem. We don't expect troughs in standard models.
I was wondering what parameter caused that?
Lack of parameter. So basically, we have only these two frequencies here. It just joins it. Astrophysically, we expect a very smoothly changing transition. It's just sparse sampling of the points that makes it look like a trough. It's not.
So we simply ignore it, I think, right? That works.
Yeah. I'll come to troughs. And this is just a more visual demonstration of how these different parameters actually impact. So the first one is the actual brightness temperature distribution, how the mean or the global signal changes, and how the power spectrum changes. And this is done by changing, say, ionizing efficiency, by changing the mean free path of the photons, by changing the virial temperature, or rather the minimum mass that's required to form halos, and so on and so forth. So we'll not get into the details of how these are dependent, but the idea is how sensitive these signatures are to different astrophysical models. So though we are detecting this, we would like to reconstruct these, which is really the actual point here. Okay, so why has it not been detected yet? None of this actually is because of everything else that comes between those epochs and us. Unfortunately, we live in a galaxy, and that really makes the whole thing very messy because galaxy is very bright in radio. So this is one of the models called global sky model, and you can see the units. These are Kelvin units, and these can be tens of thousands of Kelvin bright, depending on which region of the sky we are looking at. And at the same time, this just shows the dynamic range of where the signals lie and where the galactic emissions lie. So there is a 10 raised to 5 orders of magnitude difference. Though this is really not the bottleneck, though the dynamic range is huge, and that's mostly because of the spectral characteristics. So from a synchrotron emission, we expect a power law-like signature, which is a smoothly varying function in frequency. And of course, there are other radioactive processes, but we don't expect a process that can imprint very fine spectral imprints, unlike what we have in 21 centimeter radiation. So if it were an ideal world and we could just measure as it is, we had means to separate foregrounds from the signal, even if the dynamic range is huge. The problem arises because of the telescope response itself, and that's really the state of the field, while every telescope is trying its hardest to address a lot of systematics that actually can have features that are there in 21 centimeter signal.
So if you take the static synchrotron emission as a, let's say the foreground emission as a template, whatever you see in a patch of sky, and you have a template of synchrotron emission and you subtract
templates are never accurate to millikelvin levels. So we have sky models to create those templates, but the thing is, we have sky measurements or all sky surveys at very spot frequencies. In the frequency band that I showed right here, we only have some 3 different measurements. Okay. And first of all, those measurements themselves have tens of Kelvin inaccuracies. And if we even use them to construct the model, it's not going to be millikelvin accuracy at all. But so really the best way to create a template is to measure it.
Right, but then again you do have the, like, it's not accurate then again, but you have these models of galactic magnetic field, like Shirkov or Farrar, let's say.
Yes, yes. So definitely we can't subtract a template, but we can fit a model. Yeah, we do that. I'll come to that. Okay. Yes, okay. Yes. So we, because of the radiative mechanisms, we know what kind of models we can employ. Yeah. The problem is the instrument again. And that basically brings us to the systematics forest. Yes.
What is the angular scale of those perturbations? The first, second slide that you showed. Yes.
These ones? These ones can be, well, in K it is like 0.1.
No, angular scale.
Yeah. So K will be, in angular scales, so we really don't need a large baseline. Even a few degrees scale should be fine.
So in your background image that you showed.
Yeah. Background, as in?
The radio background, galactic radio background.
Okay, yeah.
The globe that you showed.
Yeah.
Here, if you look at the galactic anti-center direction, isn't that much fainter?
Actually, galactic angular scales can be larger if you are looking at broad synchronous features.
No, if you avoid galactic plane, galactic center, and all of that, just look at this direction.
Yes.
The southwest.
Yes.
Southeast.
Right here.
Is the background like factor of 1,000 smaller there?
Yes, and we have preferred regions on the sky where we would want to do this, which are colder. But and we have tried to take advantage of angular information, but it has not been successful yet, simply because we don't even know the foreground model at those angular scales accurately. But definitely, which regions we should observe is a very strong preference there, especially for power spectrum measurements.
So, consider that you 10 to the power 5 might come down to 100.
Not 100, but 1,000. Yeah, for some regions.
So if you did do this, then would that line come down significantly?
Right, it can come down a factor of 2.
Factor of 2.
Yeah.
That's fine.
Yes, and really even with 10, as I said, 10 raised to 5 is not a problem. The problem is other imprints that are on top of this, which is what I'll talk about, which is we have several sources of systematics from our own telescope which really can't be avoided, starting with the antenna, because antenna has a specific field of view, and in most of the instruments it changes with frequency. And that can introduce a lot of features that are intrinsically not there in this power law structure. And if we want to correct for such things, we really need a very precise model of the sky as well as a very precise model of our field of view or the beam. And a lot of people, especially Kavita here, does a lot of electromagnetic simulations to understand these properties. Then down the receiver chain, we can also have standing waves forming because our impedances are not exactly matched. And those standing waves in frequency domain again have spectral modes that are there in 21 centimeter signal. We can also have self-generated interference, and especially for ground-based experiments, we also have external interferences from other sources. So all these different forests of systematics kind of complicate the situation. And this is, I'll come back to that later, the plot that shows this, which ties up with the dynamic range. Yeah.
So when you say there is impedance mismatch, two questions. First of all, why does it happen? And secondly, how much mismatch is there?
Right. So I'll probably touch upon this later when I talk about receiver and subsystems. Thanks. It's mostly because of our antenna response. Other things are fairly matched, but antenna is very hard to match across a very big frequency bandwidth. Yeah, so this basically in the blue shows the synchrotron radiation, and the red shows the 21 centimeter signal, the units being this side. So you can just contrast the numbers here. If we just had these without any instrument artifacts, even if the dynamic range is huge, we can subtract out a very smooth component and completely get rid of the foregrounds. While if we add the two, which is the real case, we will be left with a lot of signatures coming from 21 centimeter signal. And we have, even if this huge dynamic range was there, we actually just got a victory over it. And that's simply because the spectral nature of the foregrounds is very smooth. So it's just like a filtering here. Now the problem arises, as I said, because of these systematic forests, and that's where most of the efforts in our lab targets at, how to basically address all these different ways in which systematics can be introduced. Systematics will always be there, but our idea is to have them so that it does not have spectral modes that are in 21 centimeter signal. So there are two these experiments that I'll be talking about. One is SARAS, which is a ground-based radiometer, and its space-based counterpart is Pratyush, which is proposed to be orbiting around the moon, conducting observations in the far side. So yeah, talking about impedance mismatch, so this is what our telescope looks like. As I said, for mean measurements, really we have a very simple system. We have a single antenna and this whole analog chain that calibrates the bandpass of this receiver by toggling between antenna and the noise source. And then at other end, we have some filtering stages that basically restricts our band, and a digital cross correlation spectrometer that computes the Fourier transform to produce the sky spectrum. The impedance mismatch arises right at this stage because we want our antenna response to be very smoothly changing, which means it should not have resonance peaks, it should not have sinusoidal ripples. That's where most of the antennas are there. So we again go with very non-conventional designs. We don't operate antennas in resonant modes, but rather non-resonant modes. And the impedance mismatch between antenna and the analog is what causes the standing waves. And we really can't get rid of it, but what we want to do is to minimize that. So basically we minimize the length that is there. So even if there is a standing wave, we are only sampling a very small part of the sinusoid and not a complete cycle. Because a complete cycle, again, spectral modes are there that are there in the signals as well. At the same time, we have other constraints, which is minimal variation in field of view of antennas, a smoothly changing transfer function. We also have some phase switching later down the chain that basically cancels a lot of systematics. We also isolate optically different subsystems in our radiometer so that the crosstalk or the backward propagation is reduced. And finally, the digital subsystem is very effectively shielded so that there is no self-generated interference there. And this design has been really come up with a lot of optimization, and this is all simulated work, which is for any given design, say antenna beam model, we have some sky models, we have the entire change transfer functions added to it, and then use this mock data as if it's a real data and try to extract signal from it. And this basically validates what kind of different antenna models and calibration models can be used in radiometer like SARAS. So based on this scheme, we have basically come up with a design that's shown here. And it's not really the first and definitely not the last. It has its own series of evolution starting off around somewhere in 2010 where we had a dipole antenna. This was in Gauri-Bidnoor. And since then, a lot of changes have happened, a lot of optimization has gone in to improve our calibration, from dipoles to monopoles, change in observing environment, and so on and so forth. And right now, the final state, SARAS-3, is what it's right here. So it's basically, as I said, there is this antenna and an analog receiver that sits just beneath it. And again, one thing that makes it very non-conventional is the observing medium. It floats on water. And that's simply because on ground, you also have stratification. So again, it ties up with the standing waves. You have different reflections at different strata of the ground. And that is very hard to model unless we really have the huge profile along with their conductivities and permittivities. Challenging task, especially because we are talking about wavelengths of a few meters here. While water is a very uniform medium, and there are only two length scales in this. One is the depth and one is the shore. So this is fairly easy to both measure and model in electromagnetic softwares. Undulation?
The water is not going to be as, sort of rigid as,
Right.
as earth, right? I mean, as ground. So doesn't that cause any issues?
I'll come to that, yes, yes. So we do expect some systematics. Is the question of what's the tolerance? Yeah. Though we have sufficient anchoring mechanisms to make it as mechanically stable as possible. Yeah.
Quick question here.
Yeah.
So we measured some conductivities, and so how were they?
Great.
I never asked you.
Yeah, and I should acknowledge Ranjani for taking pains of doing that.
We should. I just wanted to know if they were good enough.
Yes. For science like this, we really want fresh water, whichever places we go, we bring out water samples that are tested, and yeah, most of the samples that we have sent across are fresh water, so they are really very useful for our antenna performance that way. But there are some challenges to the ground-based experiment. One is radio frequency interference. I'll probably have to run through these slides, but radio frequency interference is known because it's all FM TV transmitters. Ionosphere is also a big deal because there is a lot of frequency-dependent refraction effects that happens. And antenna seated on a dielectric medium, whether it is ground or water, also has its interactions. So all these are very unique problems to ground-based experiments. And that was the reason we proposed another experiment, and they are supposed to go hand in hand. This is called Pratush, which is proposed to fly in space. And the idea is, the architecture is very similar, but the idea is to compactify all of this to make it into a single payload unit. And I'm very happy to say that we have already completed our laboratory model. So these are different subsystems: antenna, the front-end receiver, and the digital electronics. All of this seated just below the antenna like this. Having said that, there are challenges unique to space-based experiments as well. We have a very small constraint, right? A very big constraint actually on mass, power, and volume. While in SARAS, we have liberties of taking things 150 meters apart so that all the interactions are minimized. That's not really the case here. At the same time, because digital system is sitting right at the antenna, we have to really shield it very well. So we have to hunt for materials that are lightweight, but also very effective in shielding these radiations. Otherwise, it can create a feedback loop. And antenna is metal, and any metal nearby will affect its property. So again, unlike in SARAS, where antenna is in isolation, observing in a very pristine environment, here all that is right below it. So when we optimize for the designs, we just can't optimize antenna standalone, but we have to take everything into account. So designs can really change if anything changes below it. So it has to be a very iterative exercise. And using this lab model we have already tested, we have done a lot of tests to assess the sensitivity of Pratush itself, and it really gives us residuals of some 60 millikelvin in a single day's run, which is very promising because that's the kind of sensitivity required for 20 centimeter detection. And we are still working on different isolation strategies that we can incorporate in a payload like this. So that's where Pratush stands. I'll switch gears and in last few minutes talk about some of the results that we have got. It's similar. It's just that here the integration time is smaller because it spends, right. So basically here we toggle every second between sky and a noise source in SARAS. While here, because again, one of the other limitations is our resources, the digital resources are fairly minimal compared to SARAS because power requirements are less. Here, every state it observes for 6 seconds. So effectively our integration time is down by a factor of 6 for Pratyush.
You can get to the same sensitivity at much
So if we
smaller
account
wall clock.
One?
Much smaller wall clock time, I'm saying.
Yeah.
But the
So if we
integration,
account,
effective integration will be the same.
Yeah. So if we account for this reduced integration time, we do expect the kind of sensitivities that we have already seen in the lab.
So what is that ratio? Like how?
6.
6.
Okay, so just talking about some results. The first results came from SARAS-2, which observed in 100 to 200 megahertz. And you might remember the suite of signals I showed before. The colored signals are the ones that it ended up rejecting. And you can see all the similar features in all these models was a very deep absorption trough. And this basically means that the contrast between the gas temperature and the radiation background is huge, which in turn means that the gas is very cold. So essentially what we ended up constraining was the X-ray efficiency of how low can the X-ray efficiency go so that these signals are completely ruled out. And this was actually one of the first experiments to be able to constrain these properties using 21 centimeter observations. Recently we have taken a second shot at it by expanding on the kind of systematics we expect and also the broader range of signals, including signals that have more deeper absorptions because of excess radio that I talked about before. And using these Bayesian techniques, we were able to constrain a lot of models where we expected excess radio background from the early population of galaxies. So this is the kind of priors we had used, and using SARAS-2 data, we were able to go down to very low amplitudes, which means most of this parameter space that was unconstrained was completely ruled out. So basically we put a constraint not just on the X-ray properties of the sources, but also how much excess radio emission we expect in addition to CMB. SARAS-3 is probably more well known, which observed on water. And this really started off with the claim of edges signal that Prabhu had mentioned of this flattened trough. And basically out of 15 hours of observations, we were able to rule it out at a 2 sigma confidence. And so this is the kind of measurements that we had got. And basically our scale factor that basically determined whether the signal is there or not was 0, which means the signal was absent at around 95% significance. Again, we have expanded on this, and now we have also probed a lot of non-standard models with the same data. And this time we have gone back to the standard models, which has some excess radio, some star formation efficiency, which is what fraction of the gas actually gets converted to stars. The circular velocity, which again ties up with the minimum mass that was required to form halos, X-ray efficiency, and optical depth. And we are able to constrain the excess radio. At the same time, we are also able to constrain star formation efficiency, which anything above 5% is ruled out at redshifts of 15 to 25. And these high redshifts are really untouched by any other observations right now. So just comparing the SARAS-2 and SARAS-3 results, again the prior range is the same, and SARAS-2 ruled a subset of it ruled out, which is in green, and SARAS-3, which observes at even higher redshift, ruled out even more parameter space. And this work recently got accepted and should be out very soon. I don't have much time, so I'll just probably skip over to a few slides. One is the power spectrum, which is again a very complementary measurements. HERA is one of the collaborations I work with, and the latest results have put a very stringent, one of the deepest upper limits on the 21 centimeter power spectrum. And this has also allowed us to probe different models. And this is really a very exciting period, because just 5 years back, we were at a stage where we were looking very differently at these global signal experiments, power spectrum measurements. But suddenly, because they are probing the same exact field, and the limits are so promising that we are able to actually put constraints on spin temperature of the gas, on the excess radio background, with these different measurements with very different systematics. So for example, SARAS lands right up here in HERA measurements, and HERA itself places limits on the ratio of the gas temperature to the background radio. So this is all very promising direction in which the field is progressing. And this is the current state of HERA, the HERA along with SARAS. So SARAS was able to rule out these excess models, and right now with HERA results, we are able to rule out even more. But where do we go from here? And that's really maybe 5 minutes. Okay, thank you. So Pratush is already in the pre-project studies phase by ISRO, and this has been like this since 2019. And in this time, we have been able to develop the lab model. And our next stage is basically to be proposing a mission in low Earth orbit, just because windows of opportunities in lunar orbit are more sparse and distant. And even from low Earth orbit, though we have RFI there, the interference, but we at least escape the problem of ionospheric effects and antenna and coupling to the ground. And that really helps us. So this is of the simulation, stating that even if we don't have FM band, if we are limited by that, we should be able to rule out a lot of standard models from LEO. And if we go to lunar orbit, where it will be more pristine, and from far side we can really just cover the full band, we should be really able to probe the entire parameter space here. So right now we are really working towards a low Earth orbit launch, and we are developing our lab model and finalizing it. Towards Saras, since last observations that happened in 2020, we have done a lot of upgrades so that its response becomes even more spectrally smooth, because that's really the key towards being able to subtract the foregrounds. And that has really yielded very good results. We have been able to get down to some 30 millikelvin in one night, which is again what we expect. And we are not really limited by systematics at this stage, and this is all what we call as maximally smooth function. Therefore, it's a very stringent criteria to be able to model a system response like that. Coming back to Urbasi's question about what kind of systematics we may expect because of antenna stabilities and all different things, and this is where Kavita has been working a lot. So we can assess our systematic uncertainties because, for example, there is a tilt in the antenna and how the beam changes, and correspondingly how the impedance changes, and what we measure may depend on these instabilities. So basically we are at a stage where we are doing all these set of simulations to understand these effects and what is basically allowed. Basically at the end of the day, what we want is to be able to extract the 21 centimeter signal. So not every movement or degree of freedom is completely out of picture, but this really gives us an idea of the tolerance limits that we can have for our not just calibration but also for our stability of the system. The last but not the least, we also need very good sites because the last site that we characterized, which were in 2020, where the deployment actually happened, we could not really use anything above 85 megahertz, and that was simply because we were limited by FM, and therefore it stopped us from probing a lot of very interesting models. So now we have taken this characterization job of going to different remote sites. The last deployment, characterization deployment happened in July this year, where we went to Ladakh, and we have already done some characterizations of the antenna performance and also the RFI environment there. I'm sure it must have been fun to be rowing boats at 5,000 meters, but this service turned out very promising, along with a very recent test science deployment we did at DG Halli here in Karnataka. So we are already in the process of getting ready for the science deployments in few months. And just to show the kind of sites that we have found, so this is the time frequency plot, which is what we use as a first stage to look at a site's loudness, frequency versus time, and all these different stripes are basically the interference signals. So you can see between around 100 megahertz, you see these bright FM lines at Gauri Bidnoor, which is expected. But the moment we go to places like Ladakh, this is all cleared up, and only what we see is maybe these satellite lines which are unavoidable from any place in the earth, but other than that, we don't see any trace of any other interference. So this is really competitive with all these radio protected zones in South Africa and Australia. Actually, some of it might be better than those. So we have more characterization expeditions, which will eventually lead to the science deployments of Saras 3 in its upgraded edition. So just to summarize, we know 21 centimeter signal is very promising, both the power spectrum and the monopole components. And we are continuously trying to address all the problems that are associated with these detections. Saras has already successfully addressed several of those, and that has led to a very strong astrophysical constraints. And next science deployments will happen very soon. And Pratush will very soon be complementing this from space, more pristine environments. Thank you.
Thanks, Saurabh, for a wonderful talk. Question?
Saurabh, I have a non-academic question.
Yes.
So when you talk about these deployments coming very soon, and when you talk about going to July, going in July to Ladakh and all, how do you get the permission to do this in different sites?
Yes.
What is your political connection?
For Ladakh especially, our point of contact is the personnel Dorje Hangchuk. He's engineer in charge at IAO, Hanle. And we should really acknowledge how useful and how helpful those people are to us. So all the permissions of going to remote sites, which are really off the tourist track, are basically done by those people. We really have very minimal association.
So they have a connection with RRI per se, or is it just your...
Very informal, yeah.
Okay,
It's very
okay,
informal.
thanks, yeah.
Yeah. So I had a very basic question about how you eliminate your models. Okay, and this is perhaps so the thing is that my understanding is once you do your corrections, your signal is flat. I mean, so here's the thing. Right now, so far, the result from all the Saras experiments is a null.
Yeah.
Right. So now we see the spaghetti of models which is out there. How does a null result help you discriminate some models over other models when you have, because this null is applied over a certain frequency span. So then how is it that some models survive and others do not? So what is your discriminator?
Yes, great question. Actually the limitation comes from our sensitivity. So basically, for example, in the last trip, we were able to use 15 hours out of 100 hours thanks to RFI. So there are these models, for example, that have these huge absorption features. And if we apply our foreground subtraction filters and all, if they were there in the data, their residual signatures would have been above our sensitivity. And that's how we say that they are not there in nature, because otherwise we would have seen them. But that's not true for, say, very low absorption models, where they, after we apply these filters, they are definitely much below the kind of sensitivity that we have. So, for example, this is 200 millikelvin sensitivity. And if a model, after surviving filters, is at 50 millikelvin, we really can't say much about them. So they are unconstrained with Saras data. But if something which is at 500 millikelvin has to survive, and if we don't see it, we can very effectively rule it out. So that's the discriminating factor here.
Okay, so this, no, this, you're saying this 21 centimeter, is this coming from the spin flip of this hydrogen atom, right?
Yes.
So if I want to see this, let's say from a tank of hydrogen gas in a lab, so what do I need to do? I mean,
it's almost impossible, because the spontaneous way it can happen is it's almost time scale of universe. So,
so can one put some like a high voltage or something, like it's impossible to do in a lab?
Yeah, we need galactic scales of hydrogen to be able to have this spontaneous transition happening. So closest we can probably see it in galaxy and not really labs.
So it's not possible to do it here?
No.
Okay.
Yeah, sorry? Low density is the key.
Low density. But that's not, shouldn't be very difficult, no, to get a low density hydrogen.
No, but the time scales are also huge, 10 raised to 15 seconds or so.
10 raised to 15 seconds for the
spontaneous transition from one to another.
Sort of good talk. Thank you. It's very interesting. And one question I have is, when you have a LEO orbit model, is it a scaled down version of what will go to the lunar orbit, or what is the sensitivity levels you expect to get, given the fact that it's close to Earth?
Yes. So for LEO, we are only focusing on 55 to 110 megahertz. This antenna itself only works between 55 to 110, after which the spectral characteristics are really not conducive to 21 centimeter science. For lunar, we would ideally want to explore the full band, which is 50 to 200. For that, we might either have to do it in a single antenna, which is challenging. We can have two antennas observing in two different bands. So the loss that we incur is basically the kind of models we can probe, which is shown right here. Right? So if we only have 55 to 110, we can basically probe things that have absorption feature at very low frequencies, which astrophysically means that the X-rays lit up or X-rays started heating the IGM very early. So those are the kind of models we can probe, but not the full set.
Okay, I have one more quick question. This, going back to the ionosphere issues, So we are located close to the geomagnetic equator.
Yes.
So how does our measurements
It kind of helps. I
Helps,
think,
okay.
yeah. If we go to even higher latitudes, especially if we approach poles, it might actually get worse. And what also helps us is nighttime. Nighttime in general, the total electron content is very low. And in general, when we look at the data, we really flag all the data that have TEC more than 20, just to be safe aside. So all the data sets that I refer to correspond to very low ionospheric conditions.
And also a related question is your antenna beam pattern, you're not seeing the zenith.
No.
So any particular reasons that you want to comment?
Yeah, this is just monopole's problem, which is, yeah, there is a null at the zenith. Ideally, we would want it to be looking at zenith so that the obstruction from the terrain is reduced. But monopoles, it's simply not possible. Dipoles, it's possible, but then dipoles have other problems using balance, for example, which are kind of an issue for us. And also because if your dipole is at a height, you have another length scale in the problem, which is from your feeding point to the ground. And that can also have standing waves, which is what was seen in Saras 1 actually. That led us to transition from a dipole to monopole. So we really don't, this is not an ideal characteristic of having a beam which is off zenith, but that's what we have to live with.
One naive question. See, looks like FM is the most troublesome thing in your observations. So, because you are actually looking at a larger frequency range of 40 to 200 megahertz here, is there some way that you can just cut out the FM region, that is 88 to 108, and just don't look at that part using a filter or something?
We do.
Then also you do that.
Yeah, so we have a notch filter because FM can be as bright as saturating the system itself.
Yes.
So we do have filter cutouts, but that just restricts the kind of models we can probe because that also happens to be around these transition regions, which is very critical for us to capture.
Right, yeah. Yes.
So yeah, in principle, like all the data that I have till now shared, all the scientific constraints have come without presence of FM band. Yes. So we do have that. Notch filter.
And then another question was regarding, you mentioned the stratification of the Earth's surface. So is it related to, you know, when you have an antenna, when you erect an antenna on the ground, the ground itself acts as the reflector of, I mean, that's how you complete it, right? The dipole, half of the dipole comes from the Earth itself.
Yes.
So is that what you are referring to, or is it some other effect?
Yeah, in some way it's related, which is, so if I take my monopole and transmit something, not everything is transmitted onto the sky. A part of it also goes into the antenna, which basically says that beam has some response towards the ground itself, which is similar to the image dipole that you are suggesting. And that is something that we can't really help with. One way people use to reduce that is to have a mesh, like a metal, so that the beam is lifted up so you don't have a lot of ground emission.
Yeah.
The problem is with that is presence of very large metals makes your field of view very frequency dependent because it's electrically very large. So it creates grating lobes and all kind of things. So there is a trade-off there.
So your wavelengths are like the maximum wavelength that you may have to handle is in meters, isn't it?
7 meters.
7 meters. So suppose, I mean, just thinking, if you really keep your antenna at a height, you know, let us say something like 20 or 30 meters or something, does this problem get resolved somehow, or?
No? Yes, so the ground coupling can in principle be resolved by going to the far field.
Yes.
Right. It need not go to space. That's where balloon experiments come in, for example.
Exactly.
Now the problem is it can't be just free floating. It needs some arrangement.
Yeah, like I mean, on the top, like, you know, you have the antennas of our Geo, BSNL and all that, which are actually sitting at a higher height.
Right.
So something similar.
So that support structure, yeah, I mean, that is fine. It's just that those transmissions are very narrowband transmissions. Now for something like this, if we want to really raise it on a mechanical structure, that mechanical structure itself will start affecting the property of the antenna, especially for a broadband measurement.
Okay. Thank you.
Just one more question. So let's say all your Saras 1 to n eliminates every curve on this. Okay, yeah, I'm just putting a hypothetical.
Yes.
Will that mean that we have to re-examine how we think of the evolution of the universe, or there will be many that will just be fodder for more models?
Yeah, no, great question. I think if we do that, first of all, we'll examine our own telescope response more. But at the end of the day, if it is conclusive that yes, these models really don't exist in nature, I'm sure there are models, for example, with magnetic fields where you don't expect 21 centimeter signal at all. This is something I think a conversation with Shiva had. But yeah, in given other observations, we really don't expect a null signal. But yeah, hypothetically, if we do, we may have to go to drawing boards again. I mean, can't help. Yes.
See, here we are dealing with these real numbers when you are doing filtering out and things like that. So we thought about going to the complex domain and looking at these signals and filtering them out.
That is some delay transforms?
Yeah.
Yeah, we are approaching that as well. Yeah. So basically doing some kind of a delay filtering. Yeah. Yeah. So imaginary part of these response also helps, because if the system is properly calibrated, the systematics, the sky should not appear in imaginary. It's like interferometry calibration. So we do sometimes take advantage of that fact to model systematics only in the imaginary component and then use that model in the real domain.
So for that, the instrument has to be reconfigured, I think.
Yes. You should not see RFI in imaginary. Yeah.
Okay, if no more questions, let's thank both the speakers.
Thanks.
And thank you everyone for attending this session.